Okay, so let's have a look at the wonderful world of elliptic curve cryptography. So elliptic curve cryptography, or ECC, was actually invented by Niall Colbitz and also around the same time by Victor Miller. Okay, so we'll look at some of the basic principles behind elliptic curve cryptography and how it can actually be used. So the first thing we'll look at is some very much the basics of elliptic curves. And within elliptic curve cryptography, we have two main curves. One is called a Weierstrass curve, and this has the form of y squared is equal to x cubed plus ax plus b mod p, and where p is a prime number. And the great advantage with this type of curve, this type of cryptography, compared with RSA and discrete logs, is that this prime number doesn't have to be that large. A 256-bit prime number for ECC is probably equivalent to something like a 1024-bit and above discrete log, or we would say Diffie-Hellman. So the great advantage is that the processing is much less, as we'll find we have some easy methods to be able to implement this. The other type of curve that we have is called the Montgomery curve. And this takes the form of by squared plus x is equals x cubed, x squared plus a x squared plus x mod p. So those are the two main curves that we actually use. So in terms of the first curve, this one here is used with a curve called SEPT 256K1. This is the one that's used in Bitcoin and Ethereum. We also get SEPT 256R1, which has been standardized by NIST as P256. But along with this, we get some other curves, such as the NIST 521 curve. This relates to the number of bits that we have in the prime number. The more bits that we have, the stronger the elliptic curve is for security. This curve here is used in curve 25519 that was created by Daniel Bernstein. And if you're interested, it has the form of y squared is equal to x cubed plus 48666 to x squared plus x, and then mod p. And in this case, the prime number is 2 to the power of 255 minus 19. That's where it gets its name from. As we'll find, this is often used in the digital signature method of EC DSA, and also for ECDH for key exchange. This method here is used in the digital signature method of ED 25519 or X 25519. And we'd often define the signature method as ED DSA. Another curve that we can use here is curve 448. This has a larger prime number than this and is more secure. So those are the main methods that we would get in terms of creating our elliptic curve methods. So how does this actually work? Well, it works because we take points on the curve. So if we take this equation here and we write it, say, in this form. So this is the form that Bitcoin uses. And we have the mod of a prime number. When we plot this curve, we get something like this. So this is the X and the Y, and the curve will look something like this. This is the analog form of it. But actually, when we implement within a finite field or with the mod P, we end up with dots. And we'll actually find out that for each valid X, there are two Y values that can result. So every point that we have that's valid within inside this equation here, there are two Y values. A bit like when we take the square root of a value, then we end up with a plus and a minus value. So sometimes what we do is that we can either store the point as an XY point, or we can store as a compressed point where we store the X value and just identify whether we have this value or this value. This is what's called a compressed value. Within this curve, we actually get compressed values automatically from our implementation. So let's just take a very simple example here and look to see if we can work out the points on our elliptic curve. So we'll take a very simple example here. So what we've now got to find is all of the XY points that will make this true. And one point is 0, 9 and 0, 28. Okay, so 3 to the power of 9 plus 7, if we take mod 37, we should find out that gives us 0. So what we call is a quadratic residue, the value will be 0 there. But we can also, if we take a value of 0 here, and this is 7, then we should find that when we take x squared or 9 squared, which is 81, mod 37, we'll get a value, we'll get a valid value there. So in this case, 9 squared is equal to 37 mod 37. So that's 81 is equal to mod 37. And if we work that out, then 2, that's 40. That's if we take 37 and 37, get 14, and then that's 6, 7. So that becomes 7. So that is correct. So when we have a 0 here, so this would be the 0 point, then we can see that 9 is a valid value of y to make that right. Also, 28 is also possible. So you can do the maths, but you should find that this is actually true. So we get 2 points for every valid point that we have. So some other points that we have. We don't have a valid point for 1 or 2, 316 and 321. So again, if we take an x value 3 cubed plus x mod 37, we should find that that will be valid there. Okay, so again, we end up with 2 points. And have a look at this. This is odd, this is even. This is odd, this is even, and this is odd. So for every valid point that we have, we actually get an even value and an odd value. So when we create a compressed point, we store when we create an uncompressed point, we would store x and y. When we have a compressed point, we basically just store the x and also whether it's a plus or a minus, or positive and negative. And when we store a point, we often put a 0, 4 in front of the x and the y value. This defines a compressed point. And it will obviously be a smaller point compared to this one. So to give you an example, for P256, our uncompressed point will have 512 bits. But if we just store the x, it will be half of that, actually 256 bits. To store the x value, and then another byte or another 8 bits to store whether it's positive, whether it's odd or even. Okay, so this is compressed and uncompressed points. But why do they matter? Well, they matter because basically what we do is, let's draw it in an analog form just now, is that on our elliptic curve we define a base point. And the two core operations that we do is a point add and a point double. So it's quite a simple operation to add 2 points together or to double them. So we end up always with another point on the elliptic curve. So if we added, say, a value. So let's say we have a private key, which is this. It's a 256-bit random value. Our public key is then here, another point on the curve equal to private times g. It's not actually times g, it's basically g added priv times. So this can be our secret key and this can be our public key. And with elliptic curve cryptography, it's not possible to be able to derive sk from pk and g. it's not possible to find the points that resulted in the current point. So this is what makes our elliptic curve cryptography work. So why is it so efficient to use this point add and point double? Well, we have what's called a Montgomery ladder. And this is a very efficient way to be able to compute this point here. If we start off with G, we take our private key and we add G up. Can very quickly find this point. So I'll show you with an illustrated example here. So let's say we have this value. This value is actually 100 in decimal. That's 4, 32 and a 64 gives 100. So with the Montgomery ladder, if we have a 0, then we double. So we'll start off with a base point G, so then we will double. Let's say we end up with 2G. The next one, we also have a 0, so we will double again to give 4G. Next one, we hit a 1. In this case, we add. So our point that we're computing, we'll call Q, we'll now add. So we end up with 4G here, and again we double. So N is equal to 8Q. Keep going, and we hit a 0, so we double, and N becomes 16G. Go up again, and this time we double, so it becomes 32G. Now we hit a 1, and it's a bit like our binary arithmetic. We will then add. So we'll add our running total of 4G to 32G, and we'll get a value of 36G. And again we'll double to give us 64G. Then for a final one, we've hit a 1. So again we'll add, and we'll end up with 64G, and 36 gives us 100G, and we'll double. What we've done here is in 1, 2, 3, 4, 5, 6, 7 steps, 4, 5, 6, 7 steps, we've computed our value. So basically it only takes the number of bit operations to compute this value. So if we had 32 bits, then it would take us 32 operations, and we'd end up with the point, and only doing either a very simple double or an add and a double. Okay, whenever we hit a 0, we double. Whenever we hit a 1, it's an add and a double. So this is a very efficient way for us to be able to create our multiplication for our point calculation. Okay, so if you remember, this is what we have: a base point, we have a private key, and we multiply that by our base point on the curve to give another point on the curve, which is our public key. This is basically our point added sk times. So let's look at the 3 main applications that we have for this: key exchange, and that is the elliptic curve Diffie-Hellman method, we can have digital signatures, and that's ECDSA and EDDSA for this one. And then finally for encryption, well, it's not so straightforward, but we have a method called ECIES, and it's a hybrid encryption method where we can use symmetric key to be able to create encryption. Okay, so key exchange, digital signatures and encryption. Let's see if we can make these work for us. So the first method we're going to look at is key exchange. Okay, can Bob and Alice communicate and then end up with the same shared key? Okay, so we have Bob and Alice, and they want to openly communicate, and even though Eve is watching, then Eve shouldn't be able to determine what the end key is that they derive. So for this, we take the Diffie-Hellman method, which is using discrete logs, and we convert them into elliptic curve methods. Okay, so the first thing they do is they agree on the curve type, so they're agreeing to the base point G. Okay, so the curve will give us the curve that we have. The main parameters that we're going to have are A, B, P, and also another value called the order. And the order of a curve is the number of actual points that are possible in the curve. So hopefully that will be quite near the prime number, but not all points will be valid. So this gives us the order. And finally, as we said, we have G. So those are the basic parameters that we have to define the curve between Bob and Alice. So then they will Bob will generate a value of B, and Alice will generate a value of A. And they won't be revealed. Now, Bob computes B, G. Okay, that's the public key, so that's BG. And Alice will compute AG. So A times G. They will then exchange them. And the key here will be B times whatever Alice sends, and this will be A and whatever Bob sends. The key there will then be B, A, G and A, B, G. Because it doesn't matter which order these are multiplied in, we end up with the same shared key between them. So this is known as the EC, elliptic curve Diffie-Hellman method, and it's used in many cases to exchange a key. We might add an E onto the end of it, and that is where we check the public key of either side to authenticate the key exchange. But basically underneath, it's an elliptic curve method that we use. So we pick the curve that we want, and then we can then apply this to be able to create our elliptic curve method. So that's ECDH that we have there. Okay, so now let's look at another one of these. And the first one we'll look at is our digital signature method. So digital signature method is where we have Bob and Alice. Bob has a public key, just like this one here, and also a private key, just like this one here. He will then have some data and will sign the data with his private key. Sends that over, and then Alice will prove the signature using Bob's public key. So can we implement this with our elliptic curve methods? The first method we'll look at is the EC-DSA method, and it was derived from the discrete log method of DSA, but was adapted to support the elliptic curve methods that we see here. Okay, so we have a message. First thing we do is that we take a hash of the message, SHA-256, MD5, SHA-1, and so on. Overall, we have n, which is the order, and n will have a number of bits associated with it. So we basically will take a hash, but then we will take the number of bits in the order of the hash to be able to create the hash value. So for this, we'll take our hash value, and then we'll just use the number of bits in n. So it could be 32 bytes or 256 bits. So we might take a SHA-512 and only take part of this hash. Next, we create a random nonce value. And this should be random for every signature that we actually create. Next, we create another point. We take the k value and then we multiply it by the base point to get the value of p. We'll end up with an x and a y value here. So the first thing that we do is that we take an r value, which is just the x point mod n, and we get an s value, which is k to the minus 1, or the inverse of k mod n, and that'll be the h plus r, and x is the private key. Okay, so x is this value here. This is Bob's private key. So Bob has signed this signature with his private key here. So then this gives us R and S, which can be sent over to Alice. On the other end, Alice will again take a hash of the message and then work out H, which is obviously just the hash of the message, limited by the number of bits in N, just as Bob had done there. Then we calculate C, which is the inverse of S mod N. And it's an easy function that we can implement in our in Python say it's the inverse of n mod n. So then we can compute u1, which is hc mod n, and u2, which is rc mod n. Okay, so we're taking the hash, taking the c value, and then we're taking the r value and the c value there. We then compute a new point on the curve, which is equal to this. And this is now Bob's public key, so let me call this y. Okay, so y is equal to x g. Okay, just like we had here. So I'll make that y there. And now if r is equal to x1, and we've got x1 and y1, then the signature computes. So let's just try that out. So we have this value here. So u1 is hc times g plus u2, which is rc times y, which is xg. So we end up with hcg plus rxc there. Let's do that again. So we have a common factor of c in there. So that becomes the inverse of s. So this becomes h and then so 1 h and then rx there. Just let's check where we are. So that's u1 is that, and then u2 is that. So we end up with that. See where we are. Okay. Okay. That should be a G in there. Okay, there's our G. And the same here. And our C becomes S to the minus 1. So next we can substitute K in there. So it's H plus RC. H plus Rx, sorry. H plus Rx over S, which is K to the minus 1, H plus Rx. These will cancel out. The K to the minus 1 comes to the top, and we'll end up with Kg. And the Kg is actually equal to the point that we computed here. Okay, so if that all checks out, then everything is fine. So this is the way that the ECDSA actually works. So now let's look at another signature method, which is a little simpler. And this is ed DSA, and it's based on a Schnorr signature method. Okay, so for this, we'll take the public key is equal to the secret key times G, as we had before, and then we'll take the hash of the secret key. Next, we'll compute our R value, which is this hash, and then we'll actually append the bytes of the message to create R. From here, we create a point on the curve RG. Next, we create our S value, and the S value is R plus the hash of R, the public key, and M, and we need to sign this, so we sign with our secret key here. Okay, so the value of R and S can be sent over with the message to provide the hash signature. Then on the other side, then Alice will compute R, public key, and the message. And then V1 as SG, and V2 as R plus PKS. And then if V1 is equal to V2, then the signature checks. We can prove this if we take that V1 is equal to R plus H of R PK M SK G. Okay, so that's equal to the S value that we had here multiplied by G. Okay, so all we're really doing is taking this value for the proof, putting it here, and then multiplying it by G. If we then take that, we get RG plus SKG, the hash of R, PK, and M all appended, and then that is equal to R, and that's equal to P, the public key, times S, which is equal to V2, as we had here. Okay, so at DSA basically takes the private key, computes a public key. We then take a hash of the secret key, and we'll then append it with the bytes of the message to get R. That is then mapped to a point on the elliptic curve, RG. S is then the hash of R, the public key, and the message, multiplied by the scalar value SK, and then added to R, which is also a scalar value. The values are sent over of R, and Alice will know about the public key, so she puts it in there, and then she'll know the message. So she computes a new value S. V1 is then SG, and then V2 is the point R plus S times PK. And the signatures check, as we've seen, if we follow this approach. Now finally, we'll look at how we encrypt. So this was a signature. This was a signature. This was key exchange. Now what we'll do is that we'll now implement encryption. And encryption isn't a natural function of elliptic curves. We've got to use a symmetric key method to be able to make it work. So for this we use ECIES, or elliptic curve integrated encryption scheme. Okay, we have Bob and we have Alice. And hopefully we'll be able to get them to communicate with each other. So for this, Bob will compute his public key as equal to his secret key or his private key times G. He then sends over his public key to Alice. Alice will then compute two values. She will take a random value, R, and work out RG. Then she will take R and multiply it by Bob's public key. Remember, this is a point. So the values of R and S are these. Then she takes the value of S and creates an encryption key. So perhaps it goes into a hashing function or takes the values of the X value, but she'll derive the encryption key from the value of S, which is R times the public key. She then takes the message that she wants to send and will encrypt that with the key that she's just computed from this value here. Alice will then also send the value of R over to Bob. Bob then computes S as SK R, which is SK R, then G. Okay, SK and G times R, which is equal to PK times R, which is the exact same value here. So then Bob is now able to calculate the encryption key that can decrypt the ciphered message and will reveal the message. Okay, so this is a symmetric key method. This is a public key method using elliptic curves, but we're using a kind of handshaking method here to be able to generate the key. But overall, it uses symmetric key here, and we're using elliptic curves to be able to generate this. Over here, we used EDDSA to be able to create a signature method based on the private key and the public key and the hash of the message. Yep. Over here, we used ECDSA as used in Bitcoin and Ethereum to be able to sign a hash with the private key and then to prove with the public key. Then we looked also at key exchange and how the elliptic curve, how the Diffie-Hellman method can be modified to be able to create a key exchange method. And then we saw how we can efficiently create elliptic curves, the typical types of curves that we have, their usage, such as with SEPT256K1 for Bitcoin and P256, and also with curve 25519, which is used with the Montgomery curve. rather than the Weierstrass curve. Then roughly how these points are made. As we saw, there are two y values for every valid x point, but some of the points don't exist, so we get the order of the curve. And we can either uncompress the points by having an xy value for the curve, which will uniquely identify it, this one or this one, or we can compress by only storing the x value and whether we have a plus or a minus. The compressed form is typical in curve 25519, but for the Weierstrass curve, we can actually identify it with a 0,4 at the start of the value, and then followed, a 0, I should have said this, we can have a 0,2 or a 0,3. 0,2 identifies even and 0,3 identifies odd. And then we have the x value. If we have a 0,4, it means that we have an x and a y, or we have an uncompressed format. Okay, so our typical curve for a 256-bit elliptic curve is 512 bits for uncompressed, but we can compress it down into 256 bits, and we add an identifier as here to be able to identify it's a compressed form. Okay, so we looked at the two basic operations that we have, point add and double, and we worked out that it's actually very simple to be able to very quickly compute the multiplication of the scalar value with a point to give us our public key point. Okay, so overall, that's been an introduction to the amazing world of elliptic curve cryptography. Thank you.